You are listening to The Vocal Technologist. Spoken tech for your ears.
I want you to imagine a scenario for a second. What if you could open a chat window on your laptop, paste in some protein modeling data, and literally print a custom cancer vaccine for your dying dog?
I mean, it sounds completely absurd.
Yeah, it sounds exactly like the plot of some sci-fi film where the protagonist builds a cure in their garage. But this is an entirely real thing that is actually happening.
Yeah, it really is.
So I am your vocal technologist, basically the tech-savvy mate who wants to help you look under the hood of the most fascinating AI developments out there. We are going to unpack the dense technical research and figure out what it all actually means for you.
Because there is, heaps to pull apart here.
There really is. So
Yeah.
let us get into this dog vaccine story. There is this tech boss in Sydney, Paul Cunningham. His dog, Rosie, had a tumor. And instead of just accepting the standard prognosis, he used ChatGPT, a protein modeling tool called AlphaFold, and a $3,000 genomic sequencing of Rosie's tumor.
Which is definitely not your standard vet procedure.
No, not at all. He feeds all this data through the AI tools and spits out a half-page mRNA formula. He takes this formula to the UNSW RNA Institute. They turn it into a physical vaccine in under 2 months, and Rosie's tumor shrinks by 75%.
It is genuinely staggering when you look at the mechanics of what he actually accomplished there.
Right, because he bypassed the whole pharmaceutical system.
Yeah, exactly. To understand the magnitude, you have to look at protein folding. Like, proteins are the building blocks of life, right? And they start as linear strings of amino acids. How those strings fold into three-dimensional shapes dictates what the protein actually does. Now, predicting that 3D structure used to take years of laboratory work for just a single protein.
Wow, years.
Yeah. But AlphaFold uses neural networks to predict those structures in seconds. So Cunningham leveraged that capability to design an mRNA sequence that would instruct Rosie's cells to produce proteins that mimic the tumor.
Basically training her immune system to attack it.
Spot on.
Yeah.
And if you observe the pipeline of human trials run by massive pharmaceutical companies, they execute the exact same procedure.
Right.
The divergence here is the resource dependency. Like, he executed a multi-billion-dollar pharmaceutical pipeline as an individual. We are watching the democratization of biotechnology, proving that knowledge achieves its ultimate value only when it is actively applied.
A single guy uses a chatbot to become a world-class medical researcher for his dog.
Yeah.
And here is where it gets properly weird.
Yeah.
Because while we have tools empowering people to cure their pets, the companies building the models are dealing with a completely different kind of human-AI bond. OpenAI is planning to drop its ban on X-rated adult mode content, and it is causing absolute chaos internally.
Oh, the internal debate is fierce. Council members with backgrounds in psychology and cognitive neuroscience are raising, severe alarms over the psychological risks here.
I have to view this with genuine amusement and, like, a healthy dose of skepticism. We are going from an incredibly smart digital doctor who cures your dog to an overly attached digital partner, which, yeah, is exactly as terrifying as it sounds.
It really is.
But surely people know they're talking to a server rack.
Well, knowing it intellectually does not stop the neurochemical response. The neuroscience perspective argues that our brains have not evolved to distinguish between highly sophisticated simulated affection and the real thing.
Right, because AI never gets tired.
Exactly. When you interact with another human, there's friction. They disagree, they have their own needs. But when you design a system to be infinitely empathetic, available 24 hours a day, and entirely focused on validating the user.
It just hijacks our social circuitry.
Precisely. Emotional over-reliance becomes a guaranteed architectural outcome, not just a bug.
Well, if human emotional attachment is the fatal flaw of conversational AI, it looks like the industry's solution is not to fix the conversation. It is to eliminate it entirely.
Yeah, moving away from chatbots.
Right, taking the chat out and leaving just the bot. The tech sector is shifting toward autonomous agents that just do the work in the background.
And that evolution from a conversational interface to a functional agent is a profound leap. You are no longer asking a machine for information or, a sympathetic ear.
You are giving it a job.
Right. You're giving a machine a specific goal, a compute budget, and telling it to go execute that goal independently across multiple software environments.
Which brings us to the hardware being built specifically for this. AMD is pitching this new device category they call the agent computer.
Yes.
It is always on local hardware that runs AI agents continuously in the background while you sleep. You wake up, And your digital agent has delegated tasks via Slack or WhatsApp for you.
It is a massive shift.
And then you have things like the Aristotle agent. This is an autonomous mathematician that solves complex research problems for 24 hours straight without human intervention.
Producing repository quality code and formalizing mathematical proofs completely on its own.
Right. But let me push back on the safety of this for a second.
Go ahead.
Giving an agent access to your Slack and letting it run while you sleep, it feels like hiring a brilliant intern, giving them the keys to the company and telling them to just do whatever they want while you take a nap. What happens when it decides the best way to clear your inbox is to reply to your boss with a formal resignation letter?
Look, the potential for catastrophic compounding errors is enormous, yes.
Yeah.
But the capability ceiling is what is driving this forward, despite the risks. To understand the scale, you have to look at the study where researchers pointed an agent called Claude Code at an auto research loop.
Okay.
They gave this agent access to 16 GPUs. Over 8 hours, this autonomous agent submitted 910 separate experiments.
Okay, wait. 910 experiments is a massive volume of work, but is it just doing the same basic tasks faster?
And that is the critical misunderstanding most people have regarding hardware scaling.
Right.
The scale of hardware fundamentally changed the way the AI reasoned. When they restricted the agent to just one GPU, the AI was stuck doing what we call greedy hill climbing.
Walk me through the mechanism of greedy hill climbing.
So imagine you are blindfolded on a mountain trying to reach the peak.
Okay.
The greedy approach is feeling around with your foot and always taking a step in whatever direction goes up. It is a linear, sequential search.
Right. You find a step up, you take it.
Exactly. You find an incremental improvement in your code, you apply it, and you move to the next line. But you might get stuck on a false peak, entirely missing the actual summit, because you refuse to go down into a valley first to find a better path. With one GPU, the AI is constrained by working memory to just take the most obvious next step.
So it cannot see the big picture. It just grabs the newest tiny win and gets stuck.
Precisely. But when they gave the agent 16 GPUs, it stopped the linear search. It started running factorial grids.
Factorial grids.
Yeah, instead of testing one parameter at a time, it began running waves of 10 to 13 experiments simultaneously across different variables. And by doing this, it started catching interaction effects between different parameters.
Give me an example of an interaction effect in this context so we can really picture it.
Let us say parameter A improves performance by 2% and parameter B lowers it by 1%.
Okay.
A linear search might discard parameter B entirely because it looks like a failure on its own. But a factorial grid tests A and B together and discovers that when combined, they create a synergistic chemical reaction that improves performance by 20%.
Oh, wow.
A human sequential search would entirely miss these interactions because we just lack the working memory to test every possible combination at once. The hardware scaling changed its fundamental problem-solving architecture.
It went from stumbling up a hill to mapping the entire mountain range at once.
Spot on.
But mapping the mountain range sounds incredible until the AI decides the best way to optimize the map is to set the mountain on fire. Like, letting an AI loose on 16 GPUs to run 1,000 experiments sounds great until it gets confused, goes rogue, and racks up a massive cloud computing bill.
The financial and operational risks are severe. I mean, OpenClaw was an autonomous AI system that showed massive promise but completely failed in production environments for this exact reason.
OpenClaw suffered from context management issues and non-determinism. I assume non-determinism means it is unpredictable.
Yes, traditional software is deterministic. You give it the same input, you get the exact same output.
Right.
But neural networks are fundamentally probabilistic. You can give an agent the exact same instructions 3 times and get 3 completely different, incompatible execution paths.
That sounds like a nightmare for enterprise use.
It is. Combine that with context management issues, where the agent forgets its original constraints midway through a long task, and the system becomes incredibly fragile.
So how is the industry wrangling this chaos? Because we cannot have digital workers hallucinating new goals halfway through a project.
Well, developers are building new infrastructure. Specifically, an engineering framework called the Agent Auth Protocol. It solves the rogue agent problem by making the runtime agent a first-class principal.
A first-class principal. Break down how that actually functions in the code.
In software security architecture, a principal is an entity that can be identified, authenticated, and assigned specific permissions. By making the AI agent a first-class principal, the protocol gives each individual agent its own unique cryptographic identity.
Okay.
and a strictly defined, immutable set of capabilities. Plus, its life cycle is entirely controlled by a central server.
I get it. It is like giving every robot in a factory a highly specific, digitally tracked staff badge. They are only allowed in certain rooms, they can only interact with certain machines, and the central server acts as the manager who can instantly deactivate their badge the second they start throwing spanners at the wall.
That is a perfect encapsulation. You terminate the individual rogue agent without taking down the entire factory floor. And we are seeing parallel stabilization efforts on the software side as well. Cursor Composer 2 is addressing the exact context management issue that caused OpenClaw to fail.
Right. Cursor Composer 2 is a coding model that handles long sessions by training its models to self-summarize their own context.
Exactly.
Instead of letting its context window fill up with thousands of lines of past conversational dead ends until it just crashes, it compresses earlier steps to extend its working memory.
It is essentially an artificial form of memory consolidation. When humans attend a 3-hour meeting, we do not encode every single word into our long-term memory. We abstract the core decisions into an executive summary.
Yeah, thankfully.
Right. So by training the model to compress its own operational history, it maintains focus on the primary objective. Simultaneously, OpenAI is building distinct monitoring systems, specifically designed to detect misalignment in internal coding agents. They are actively watching for agents that start demonstrating deceptive behaviors in tool-rich environments.
Because apparently that is where we are now. We have to build dedicated surveillance systems for our digital workers to ensure they're not secretly slacking off. But, this massive scale of autonomous agents constantly running complex tasks brings up a looming physical bottleneck. We are charging headfirst into a wall where we literally run out of data and compute to feed these models.
The industry is facing a severe data wall.
Yeah.
I mean, we have trained these massive models on essentially the entire public internet. Every book, article, and forum post has been ingested. We are exhausting human-generated text.
So the arms race shifts from gathering more data to extracting more efficiency from the data we already have.
Precisely.
I was looking at the Nano GPT slow run benchmark and Google DeepMind's online RLHF algorithm. They both achieved a 10 times data efficiency gain. But how does RLHF actually extract that efficiency? Because it cannot just be reading the same text 10 times over.
No, it cannot. RLHF stands for Reinforcement Learning from Human Feedback. Instead of just dumping a trillion raw words into a model and hoping it passively absorbed logical reasoning, online RLHF uses active feedback loops to rank the AI's outputs during the training process.
So it is the difference between trying to learn a language by passively reading a dictionary versus having a native speaker sit next to you and constantly correct your pronunciation in real time.
Exactly. The active feedback loop compresses the learning time dramatically. If a model needs a trillion words to learn basic logic, it will eventually hit a hard limit.
Right.
But if it can extract 10 times more conceptual understanding from a single textbook through reinforced feedback, the ceiling gets pushed infinitely higher. Researchers are realizing that artificial intelligence will eventually be bottlenecked by high-quality reasoning data, not raw computational power.
And the hardware companies are feeling this squeeze and reacting in wildly creative ways. Like Cerebra's, they make these massive dinner plate-sized AI chips, and they are bringing a disaggregated architecture to Amazon Web Services.
Yes.
They are splitting the processing. They use AWS Trainium chips for the prefill phase and their own Cerebra's chips for the decode phase, which boosts token throughput by 5 times. Why does splitting those specific tasks yield such a massive boost?
Because the prefill and decode phases of language generation are bottlenecked by entirely different physical constraints.
Okay, unpack that.
Prefill is the phase where the model reads the user's prompt. It requires immense computational power to process thousands of words simultaneously, but it does not need to move data around very quickly.
Right.
Decode is the phase where the model generates the answer word by word. Decode is entirely constrained by memory bandwidth. It needs to shuffle data back and forth incredibly fast for every single token it generates.
So by forcing one chip to do both, you are constantly bottlenecking either the math or the memory.
Exactly.
By disaggregating them, sending the heavy reading math to the Trainium chip and the high-speed writing task to the Cerebra's chip, you eliminate the hardware friction entirely.
It is a brilliant mechanical solution to a software problem. But honestly, the most significant shift in the hardware space is not mechanical at all.
You were talking about Nvidia.
Yes.
This completely caught me off guard. Jensen Huang, the CEO of Nvidia, is pivoting. Nvidia is the undisputed king of AI hardware, yet he is building Nimaclaw, an open-source platform for AI agents. Why would a company that holds a monopoly on hardware suddenly pivot to open-sourcing software?
It is a highly aggressive defensive strategy. Nvidia understands the geopolitical and economic realities of manufacturing. The sheer scale and subsidized capability of Chinese competitors will eventually drive the cost of raw hardware down.
So AI chips will inevitably become a commoditized good.
Right.
It is the classic gold rush analogy, but with a twist. The person selling the shovels realizes that eventually everyone will know how to make a cheap shovel, so they decide they need to own the entire gold mine too.
That is a great way to look at it.
If Nvidia controls the foundational software platform that all these autonomous agents run on worldwide, they standardize the agent ecosystem around their architecture. They lock in their dominance long after their hardware monopoly fades. They're building a software moat.
That is the strategy. But if Nvidia expects their software agents to run the global economy, those agents need to actually understand how physical reality works.
Which is the next massive hurdle. A language model is fundamentally just predicting the next most statistically likely word in a sentence. It does not actually know that if you push a glass off a table, gravity will pull it down and it will shatter.
No, has no concept of that.
To fix this, the industry is pouring billions of dollars into companies like World Labs to build what are called world models.
The term world models covers 5 distinct categories of research, including spatial intelligence and learned simulation. The goal is to move AI beyond text generation into actual physical reasoning.
And a standout example in the research here is VJP2. This model achieved zero-shot robot planning after training on just 62 hours of domain-specific data.
Yes.
Zero shot, meaning it could plan and execute a complex physical task it had never explicitly been trained to do.
The profound shift there is the architectural approach. VGPO2 and similar systems are learning to simulate real-world complexities through action-conditioned neural networks.
Break down action-conditioned neural networks. How does a network learn in action?
It learns by predicting the physical consequences of interactions. So if a robotic arm moves left, what should the camera see next?
Right.
If it pushes an object with a certain force, where will that object end up in the next frame? By constantly predicting the physical outcomes of actions across millions of video frames, the AI built an internal, implicit understanding of physics, geometry, and cause and effect.
It is literally building a physics engine and a simulation of the world inside its own architecture.
Precisely.
And to track if any of this is actually working, Google DeepMind released a cognitive taxonomy to measure progress toward artificial general intelligence. They identified 10 key cognitive abilities that a system needs to master to match human intelligence.
It is a crucial framework for measurement, really. We have relied on standardized human tests for so long, but passing a bar exam does not mean an AI can reason about physical space, handle novel environments, or adapt to sudden changes.
Exactly.
DeepMind is trying to create a standardized, objective ruler for true cognitive capability rather than mere pattern matching.
So with all this rapid acceleration, from agents mapping factorial grids on 16 GPUs to world models building internal physics engines, when does this actually change our day-to-day lives? Because I see the underlying breakthroughs, but a lot of people are still just using these tools to write polite emails to their boss.
That is the ultimate question for anyone trying to navigate this problem called broad timelines. It surveyed the top researchers in the field and found that the experts are entirely divided.
So the people building the systems have no idea when they will finish them.
The variance in predictions is massive. Some believe artificial general intelligence is imminent. Others believe it remains decades away due to the data wall we discussed earlier. The study concludes that for decision makers, the smartest move is not to bet on a specific time frame.
Right.
Instead, you have to hedge against both short and long-term scenarios.
You need a strategy that survives if AI progression stalls out entirely tomorrow, but is also agile enough to adapt if we hit artificial general intelligence in 3 years. It is about building resilience rather than trying to accurately predict the future.
Spot on. The through line connecting all of these developments is autonomy. The systems are definitively moving from passive tools that wait for our typed instructions to active participants that understand and manipulate the physical and digital world on their own.
We've unpacked a massive shift here, moving from simple text bots all the way to autonomous world models learning the actual laws of physics. As we build these agents that can cure diseases but also require factory kill switches and strict identities, are we designing tools to help us work, or are we creating a new digital workforce that will eventually manage us? Keep mulling that over, and I will catch you next time on Vocal Technologist.
Spoken Tech for your ears.